So thank you very much for the opportunity to speak at this wonderful conference. It's really an honor. So today I'm going to be talking about some work we've been doing, or I've been doing with a number of excellent collaborators that I'll mention throughout, on trying to connect certain ideas which go in the name of conformal collider physics with trying to understand real-world collisions, for example, at the Large Hadron Collider. And so the goal of this talk will be to give kind of a broad overview of this these ideas. And I'm going to try and purposely emphasize the connection with experiment, which has become particularly interesting in the last 6 months or so. And so my hope is to convince you that by phrasing collider physics question in this kind of conformal collider way, this really opens the door to being able to use a lot of very nice amplitude or conformal field theory techniques to answer questions which are relevant to real-world collider physics and to better understand the standard model. So as everyone here is very aware, since I guess the beginning or the introduction of the S matrix, there's been tremendous progress in the understanding of exclusive scattering processes. And so this is probably the most exclusive event display from the LHC. And so particularly in perturbation theory, we now have very efficient ways of computing these things. We have a very good understanding of their analytic structure, a huge amount of multi-loop perturbative data. And the very kind of practical outcome of all this was very nicely described in Lorenzo's talk yesterday, namely the ability to kind of accurately describe very complicated scattering processes with many particles in the final state. So for example, many Higgses or many W bosons, and we'll compute very accurately these cross-sections over orders of magnitude. But in the complete kind of opposite regime of this very exclusive scattering process, we have these kind of very high multiplicity collisions at the LHC. So this is a kind of completely complementary regime. And so there's different ways that this can physically occur. So one is you just have collisions with energies that are much, much larger than the kind of mass of the particle in your theory. So this is, of course, physically what's happening in QCD, and it's giving rise to these very impressive event displays like this. And at the kind of extreme level of this, one has just conformal field theories, where if you kind of ping your system, you just have some kind of flux propagating out to infinity. And so, of course, there's kind of a continuum of cases between the two of these. And so depending on where you are, it may prove useful to, for example, cluster your particles into jets to mimic some kind of quasi-exclusive process. But it's also very nice as a way of kind of organizing one's thinking to take this limit of conformal field theories and to try and understand what are the good questions to answer and how we talk about kind of collider physics events in this conformal field theory limit. And so in this case, you kind of switch from looking at the exclusive S matrix elements to good observables being kind of correlations in energy flux, which you compute at, for example, null infinity if you're in a conformal field theory or have massless particles. And so the kind of big picture question which one wants to answer is how do we characterize a theory using just these asymptotic fluxes or this asymptotic data? And there's kind of two ways, either from the theoretical motivation or the phenomenological motivation, that one can kind of think about this question. So from the purely theoretical motivation, one could just ask kind of what is the space of observables at null infinity in some conformal field theory? So what are the well-defined observables? How do you manipulate them? And how do you, for example, relate them to standard ways of talking about, for example, CFT data in terms of local operators and scaling dimensions and OPE coefficients? And this is also useful for understanding how do you constrain theories in the absence of having a well-defined S matrix or local operators, where you have very powerful, for example, bootstrap techniques. On the phenomenological side, there's also very clear phenomenological motivation, because this is literally what one does in a collider physics experiment. And so we get out these huge sprays of particles, and what we want to understand is how to relate, for example, measurements that experimentalists make to parameters of the underlying microscopic theory. So for example, from this spray of particles coming out, you want to be able to precisely determine, for example, the couplings of the theory or some transport coefficients or other kind of microscopic parameters of the theory. And in particular, you also want to do this in a way which is kind of theoretically nice. So these are very complicated collisions, and you want to be able to identify features which can be computed, for example, to high precision, or some universal features which you can really understand from the underlying quantum field theory. And so in my opinion, this kind of wealth of collider data provides a kind of very nice testing ground or playground for kind of sharpening these ideas, and it also provides a kind of metric of how well you can do in trying to understand standard model phenomena at collider physics. And so of course, I have to, since George Sturman is talking next, it's important to emphasize that this is something that people have been studying for a very long time. And so in particular, this is a very similar set of questions to what people were asking after the discovery of asymptotic freedom, where one wanted to understand what observables could be computed in perturbation theory in QCD, or in other words, what observables are infrared and collinear safe. And so one thing which was proposed, in my understanding, in 1975, so only about 2 years after the discovery of asymptotic freedom, is that you can measure the expectation value of the energy flux, which I'll denote in this way, at some specific angle on the kind of sphere. And so to my understanding, the first time that such a kind of operator measuring, which at this time was called as angular energy current, was proposed was in this 1975 paper, where Sturman showed that this could be computed in perturbation theory. And then this was kind of generalized to these multi-point correlations a few years later by Basham, Ellis, Brown, and Love, where you can kind of take correlation functions of these different energy flux operators on the sphere. And so if you do this, for example, for this 2-point correlation function, you get this famous, or in a weakly coupled theory, this famous 2-peak distribution, which looks almost exactly like the citations per year, with the hope that it doesn't just end right here. And so this is now being kind of formalized over the years. So this isn't a very particle physics language, or kind of where you have discrete particles coming into your detector. And over the years, since I guess this is now almost 50 years ago, it's been formalized into increasingly formal and a kind of operator language. So in the kind of 90s, in particular by Korchemsky and Sturman, this was rephrased into kind of an operator definition in terms of the stress tensor, which was then really put to very powerful use by Hoffman and Maldacena. And so since this is now expressed as a kind of integral or null integral of the stress tensor, this allows you to kind of, for example, compute these objects at strong coupling or relate them to local operators in a conformal field theory. And so now this is realized as just one particular example of what is referred to as a light transform of the stress tensor. And so these ideas have been massively generalized over the years. And so these objects take a kind of interesting position, intermediate position between scattering amplitudes on the one hand and correlation functions of local operators on the other hand. So of course, the reason amplitudes are nice for describing scattering experiments is they have kind of things going off to infinity, so they're boundary observables. But the kind of slight problem is that they're infrared finite, or they are not infrared finite if you have massless particles. Whereas correlation functions of local operators are very nice and kind of non-perturbatively well defined. But of course, they don't typically have the operators off at infinity. And so these energy correlators are kind of an intermediate object, which is kind of the best in some sense of both worlds. And it's also very nice because you can use techniques from the amplitudes world and use techniques from the correlation functions world and kind of really combine them to make interesting statements about real physical observables. And the other thing which is very nice about these is they provide a very nice example of observables which are well defined at weak coupling, strong coupling in a conformal field theory with gravity, et cetera. And so it's very nice kind of intermediate ground for making connections between different areas. And so as I said, these are now known to be part of a much wider class of what are referred to as detector operators. And there's been a lot of recent progress in trying to understand the classification of these detector operators and their algebras and operator product expansions. And so what one would like to do in kind of an ideal world is that one could take some very complicated detector, like in this case the CMS detector, and kind of decompose it into elementary detectors and manipulate these just like we do local operators in a conformal field theory. And so, for example, one would like to understand their kind of symmetry algebras and their operator product expansion, and this would allow us to very efficiently compute this type of observable. So from the perspective of phenomenology, these kind of advances are very nice because it's really kind of, on the one hand, you can actually use, as I'll show, measurements of these observables to tell you interesting things about the structure of these correlation functions. And on the other hand, these are very nice ways of thinking about what one should be measuring at collider physics experiment. And so one can really use this refined understanding to better understand the standard model at collider experiments. Okay, so how does one do this at an actual collider? So of course, again, this has a very long history. And so the conceptually simplest case is to study energy correlators in some state just produced by a local operator, which I'll just call O. And so a very nice, or an actual realization of this is, for example, electron-positron colliders, where you can literally do this exact experiment with the electromagnetic current. And so this 2-point correlation function was measured quite long ago at LEP. So it's shown here, where you see the enhancement at 0 and at pi. And so this has been quite accurately computed. So it's been computed analytically, and I'll discuss these calculations later, in QCD and next to leading order by Lance Dixon and Hua Jing and collaborators. And the kind of n equals 4 analog of this has been computed analytically in next to leading order by this group here, and then at even next to leading order by these people here. And so I also forgot, unfortunately, to cite the chair of my session, who did the very nice calculations at next to leading order numerically of this object in QCD. And so this object is is very well understood, and you have quite precise understanding of the comparison to data. But of course, from this perspective of really trying to kind of explore this relation to conformal field theory and measuring, for example, multi-point correlation functions or their kind of operator product expansion, this is a little bit unsatisfactory because these are at very low energy. So if you look at these jets, they have kind of 3 or 4 particles in each jet. And so you can't really measure, for example, like a 10-point correlation function or even a 4 or 5-point correlation function because they have very large corrections from hadronization. And so this is where the kind of new very high energy colliders, for example, at the LHC, and this transition from kind of GeV scale to TeV scale or multi-TeV scale really provides access to a very new and interesting regime of QCD, where you can really use these very high energy collisions to ask and measure a lot of interesting questions about the structure of these energy correlator type observables. And so in particular, the questions one can kind of ask is, can we use, for example, this very high energy data to test this operator product expansion or the kind of scaling anomalous dimensions of these detector operators in some kind of quantitative way and actually test some of the predictions that have come out of the conformal field theory world? Can you measure the full shape of higher point correlation functions? So for example, here's some little 4-point correlation function inside a jet. And also, can you measure, for example, these correlators on more complicated states? So for example, in the quark-gluon plasma with top quarks, or understand the effects of confinement. And so what I'll try and show you is that yes, you can absolutely do this. And I think it's also very important to emphasize, and this was very nicely emphasized in Lorenzo's talk yesterday, that this is something which is really kind of unique to these collider experiments. So of course, one can try and also measure, for example, these energy correlators in some condensed matter systems where you have some conformal symmetry, but this is extremely hard to do. And so these colliders are just very interesting experiments and really allow you to probe generic properties of quantum field theory in a very interesting regime. Okay, and so what I'll try and show you in the talk is a lot of progress which has come out over the last 6 months in really kind of bridging some of these theoretical ideas and experimental ideas and kind of measurements of these correlators, which I'll explain in detail, at a huge variety of different experiments. And so this really allows us to kind of understand very detailed aspects of these correlation functions in a really neat regime where we can apply perturbation theory and understand these things quite precisely. Okay. So just as an outline, I'm going to try and highlight kind of 3 features of different kind of work that's been going on in this area. So first, I'm going to discuss some scaling behavior, and how one can very nicely measure the kind of operator product expansion limit of these correlation functions and very accurately compute the scaling behavior, which can be very nicely measured in experiments. And you can actually use this to extract the value, for example, of the strong coupling constant. Then I'll show that one can actually measure the shape dependence of higher point functions. So this is, for example, a 4-point function inside a jet. And you can actually kind of map out the space of these correlation functions and kind of just play with them and study, for example, operator product expansion limits or spinning operators inside them. This is kind of a really neat playground for higher order perturbative calculations. And then I'll show some kind of phenomenological applications of where one can try and apply these ideas to better understand more complicated systems. So for example, this quark-gluon plasma case that I mentioned before. Okay, scaling behavior. So from a collider physics perspective, a kind of very nice example of a very clean relation between measurements in macroscopic systems and microscopic parameters of the theory is the Euclidean OPE, where you can consider the behavior of operators and relate scaling behavior to certain anomalous dimensions of your theory. And these can be very nicely measured in, for example, the measurement of critical exponents as you approach or in critical phenomena. And so one would like to try and understand, or if one can have a similar analog for collider physics. And so one of the very neat things which came out of thinking about this conformal collider physics is that these energy flow operators, or more generally these detector type operators, admit a form of a Lorentzian operator product expansion. And so I'm not going to go too much into the details, but the idea is that much like a standard OPE, you can kind of bring two of these detector operators, which are these null integrals, together and expand them over some more general set of other light ray operators. And so in particular, what this predicts is a universal scaling behavior as you bring these two operators together, which is governed by in particular, the anomalous dimension of these light ray operators. And so this can be derived also in more generic, in particular in QCD, non-conformal theories, using factorization theorems, which you did with Lance, based on, or in kind of generalizing earlier work, or very nice work by Veneziano and collaborators. And so this really allows one to compute this systematically to high orders, including, for example, also beta function corrections. And so I'll just kind of write it schematically as this, but I'll emphasize that this can be done in kind of real world QCD systematically. And so the very nice thing about this is that it predicts a kind of universal scaling behavior in the correlations of energy flux. So for example, in this 2-point correlation function of energy flux, as you bring the detectors together. And so this is a very nice feature which you could try to look for in collider physics experiments. And so there's this nice exchange when this was originally, when this was originally proposed. So this was originally proposed in this paper shown here. And when there was this, when this was presented, there was this very nice exchange, which is copied here verbatim, where this was kind of described, and then Polchinski said, well, there's a huge amount of QCD data out there. Why haven't people just gone out and looked for this very nice scaling behavior? And there was this response, which is people don't do this. I haven't figured out why they don't, and I think they haven't just thought about this. And so this is not 100% historically correct, but it's at least true that this was something that was never measured at the LHC until last year. And so what I'll show you is that we can really do this very nicely in very high energy jets and observe exactly this scaling behavior. And so I won't go through the details of this, just like in the talk yesterday, where one kind of skipped over the details of this factorization, but I just want to emphasize that one can really do this in a real-world LHC collision, taking into account all the experimental realities. And so we're not sweeping anything under the rug when we actually do this calculation. And you can derive a kind of full factorization theorem which combines kind of ideas from this Collins-Soper-Sturman factorization with this light ray operator product expansion or collinear factorization. And so essentially what one needs to do is to evaluate one-point functions of these correlators in some complicated state which is defined using some jet algorithm. And so this is what you compute in perturbation theory, and then you can use the nice understanding of the scaling behavior of these anomalous dimensions to predict very nice scaling behavior inside real-world jets at the LHC. And so in the last 6 months, this has been measured very nicely in jets by a whole bunch of different collaborations, going all the way from 15 GeV up to about 2 TeV. And so this is a very nice experimental measurements, and it's kind of a realization of this detector operator product expansion. And so it's hard to read these, but this is just displaying a whole bunch of different experiments that have measured this, and you see this very nice power loss scaling behavior here as a function of the angle. And so this is just a reflection of the center. As you bring the operators together, they have this nice scaling behavior going up. And so in these plots, this is largely, so this is compared here against a calculation of different orders in perturbation theory. But in these plots, this is largely dominated by the kind of classical scaling behavior. And so it just kind of goes, as you bring the two operators together, with a kind of 1 over theta power law behavior. And so one could ask, can you actually measure these things precisely enough to extract the different anomalous dimensions of the operators which appear in this light ray operator product expansion? And so one way which one could do this very nicely is that you can take ratios of different endpoint functions. So one thing which one could derive either from this light ray operator product expansion or from QCD factorization is that if you take a generic endpoint function scales with the twist 2 spin, or a generic, or if you take j minus 1 of these operators, it scales with the anomalous dimension of a twist 2 spin j operator. So essentially what you're doing is you're just slicing across the Reggie trajectory at a particular spin, at a particular spin j. And so one thing which you can do is you can take a ratio of these j minus 1 point correlators to this 2-point correlator. And so when you do this, it essentially cancels the classical piece. And what you get access to are scaling behavior associated to the difference in anomalous dimensions. And so you can really kind of map out the structure of the anomalous dimensions at different values of spin on this Regge trajectory. And so this is a plot of these energy correlators in real data for the kind of 6-point over the 2-point, 5-point, 4-point, 3-point, and so on. And so one can see that you get this very nice scaling behavior as a function. Now this angle here is called RL, just in Hadron Collider units, but this is just the scaling as a function of the angle. And so this would be 0 in the classical theory, and so this is really probing just the spectrum of these anomalous dimensions, which is very nice. And you can also see, for example, that the Regge trajectory is monotonic, and that's why these things get steeper and steeper as you go to higher point correlation functions. And so this gives you direct access to the kind of spectrum of these twist-2 light ray operators from the asymptotic energy flux. And the thing which is very nice is that you can do this in a very complicated experiment. And because you're accessing this kind of very universal feature, you see these beautiful power law scalings. And so one thing which has been done just in the last couple months is that this has been measured extremely precisely inside very high energy jets by the CMS collaboration. And so these are plots at different energies of the jets, going all the way. So this is already quite high energy, particularly compared to LEP, up to close to 2 TeV. And so what this is measuring is this ratio of this 3-point correlator to the 2-point correlator as a function of the angular size of the correlation function. And so this is predicted to scale as this particular difference of the twist 2 spin 4 and spin 3 anomalous dimensions. And so you can see that it has this very nice, for all the different energies, this very nice scaling behavior exactly as predicted. And so this is compared with these very nice calculations here, which actually use the QCD anomalous dimensions at 3-loop order. So these are very precise calculations, and they're beautiful quantitative tests of just generically quantum field theory and also QCD in particular. And so one can ask kind of what can one do by very accurately measuring these slopes. And so just like how one extracts, for example, the anomalous dimensions or critical exponents of the Ising model, here you can actually just extract these scaling exponents. And because they're expressed in terms, at least perturbatively, in terms of the strong coupling constant, you can use this to actually extract the value of the strong coupling constant. And so by doing this, they were actually able to extract the strong coupling constant at 4% accuracy. And so this is just a comparison of this technique compared to some of the other CMS measurements of alpha S. And so this is the new measurement coming from these energy correlators. And so you can see it's kind of in the ballpark of other very well-established techniques. And so in particular, the more precise ones, which are coming from for example, from ratios of 3 to 2 jet events, these really use the full kind of next to next leading order 2 to 3 hard functions. And so these are something which are not included in this calculation, and so it's something that could definitely be improved more. And so it's very, in my opinion, promising that one can kind of extract the strong coupling constant at a kind of record accuracy using this kind of very different approach. And so already this is the world's most precise alpha S measurement from jet substructure. And this is kind of a very new thing, and so there's lots of ways to improve it. And so also just for fun, this is a comparison of some of these measurements on the last plot or on the last page, all shown on one plot. And so you can see very nicely that the scaling exponent changes as a function of the energy. And so this is, of course, just the running of the coupling in QCD. And so it becomes weaker and weaker or flatter and flatter as you go to higher and higher energies, and you get increasingly asymptotically free. And so as compared to the CFT, it has this very nice kind of scaling or energy dependence of the critical exponent, which is kind of fun. And so I think this is a very clear target for improved perturbative calculations to try and better extract the strong coupling from this. Okay, so scaling is very nice, but one also wants to go to higher point functions and energy flux. And so for this, there was originally much less known. So unfortunately, there's even better things which are known, for example, about the cosmic microwave background. So of course, why do you want to measure higher point functions? So one of the reasons you want to measure higher point functions is they really probe detailed aspects of the underlying microscopic interactions. So for example, there's this kind of classic picture in the CMB that you measure, for example, 3-point functions, and this allows you to kind of distinguish different models of inflation. And so one thing one can ask is, what is the structure of higher point correlation functions of energy flux, for example, inside jets at the LHC? And this is something which, unfortunately, are not really being addressed, at least at weak coupling. So there's these very impressive strong coupling results. So there's an expansion in the inverse coupling by Hoffman and Maldacena using ADS-CFT. But so here the leading result is 1, which just means it's a completely flat distribution plus little ripples. And so this is, of course, very different than what you'd expect in QCD, which is kind of spiky in energies. And so now there's this huge wealth of techniques from computing perturbative scattering amplitudes, which can be applied to kind of just start computing these multi-point correlators and exploring how they behave at weak coupling. And because these are kind of IR finite observables which are defined in 4 dimensions, one can hope that one might find some very simple structures and that they're a nice kind of playground for perturbative calculations. And so I'll just mention the kind of 2 approaches which people have used to performing these calculations. So the first is to use local operators involving, or correlation functions of local operators involving the stress tensor, and then just directly applying the light transform. And so this was pioneered in these papers by Korchensky, Sakachev, and collaborators. And so this has been most efficiently applied for the 4-point function in n equals 4, where you can relate the stress tensor to scalar operators, and so this drastically simplifies the calculation, and a huge amount is known, and so that's how one was able to get these very nice NNLO calculations of the 2-point function in n equals 4. And so this has also been explored in QCD for the charge-charge correlator, but there you actually have to deal with tensor structures, and so it's much more complicated. And so this has not been practically applied to higher point correlation functions. So the other approach is to just use perturbative phase space integrals using squared form factors. So you can square a form factor which produces kind of n particles, and then you just integrate it over the phase space, keeping certain directions where your detectors are fixed. And so this has been the approach which has been very practical, particularly in QCD, and also for computing higher point correlation functions. So this has been used in all these, so in the 2-point calculations in QCD, and as well as I'll mention in a second for going to 3-point and even 4-point in QCD, or sorry, in n equals 4. And so this is the kind of approach for studying these correlation functions which has persisted particularly for higher points correlation functions. And so the full correlation function is a very complicated object, and so it depends on all the kind of angles between the different detectors. And it also is very dependent in general on the particular source which you use to produce the state. But there's a very nice limit which one can take, which is the collinear OPE limit. So instead of just this 2-point OPE limit which I described before for the scaling, one can take an OP limit where you take all these cross ratios to 0, but keeping them their ratios generic. And so you're kind of scaling them all to 0. And so in this case, it becomes a function of 2 n-2 variables, and it's independent of the source, again, by this kind of operator product expansion idea. And so the thing which is very nice when computing these in perturbation theory is if you try and just compute them, what you get is a finite integral, at least at leading order, over universal splitting functions. So you have an integral like this, where this is just the conservation of energy, and you just have to integrate this, since the angles are fixed, against the universal splitting function. And so this is a very nice object, which one can hope to explore at higher orders. And because it's really just probing properties of the detector and not the source, one could hope that it has some very nice structure. And so, of course, the other motivation for this is that this is the limit that can be physically measured inside high-energy jets at the LHC. So, for example, if you have some very high-energy jet, if you're really measuring a 4-point function, it's going to be at very small angles in the jet. So I'll come back later, where you can, in E plus E minus, you can measure these at generic angles. But at least for the LHC, you have this very nice collinear limit, and this is what one can hope to try and probe. And so this is something which is very simple, and so unfortunately it wasn't explored before. And so one can just start exploring these and building up in perturbation theory. And so the first correlator with some non-trivial shape dependence in the collinear limit is just this tree-level 3-point correlation function. And so one can just do this, and this is compared to modern amplitudes calculations extremely simple. So it's just it's shown here for the case of n equals 4, and is expressed in terms of just some single-valued polylogarithms. And so the thing which was kind of very nice from this is it actually gives a very simple answer. And so one thing which is very nice about these calculations is because they're directly of a physical observable, so there's no kind of cancellation of infrared divergences or anything, you just literally plot this function, and it really shows you the kind of patterns in your energy flux in your detector. And so you can actually just go out and measure, for example, this 3-point function inside high-energy jets at the LHC. And so in this case, this is normalized to a particular product of 2-point functions to make it a non-Gaussianity. And so you can see that it kind of has this interesting shape as a function of the shape of the 3-point function. So these are a little bit hard to absorb, but up here is kind of an equilateral triangle. Down here is this flattened triangle, and then these are some kind of OPE limit down here. And so one can just plot this function which I showed on the previous page, or at least it's analog in QCD, and so you can see that it gives a very nice kind of qualitative description of this shape. And so you can really start playing with these higher point functions inside jets. And so kind of motivated by this very nice structure at 3 points, this was then extended to 4 points, and so this was really led by Kai in n equals 4, and just by directly integrating a very compact expression for the 1 to 4 splitting function. And so one could obtain a very nice result just in terms of weight 3 polylogarithms. But I think here there's still a lot more structure to be explored in the kind of simplicity of this answer, as well as extending it to QCD using the known 1 to 4 splitting functions. And so to kind of motivate extending to higher points, I want to show that these are also really measurable in data. And so what one can do, or first I want to kind of show the structure of these. So this has a very nice kind of intricate pattern of the correlations in energy flow. So now because of the full 4-point function, you have to kind of take specific projections of it. But one can do kind of fun things where you take, for example, 3 points in an equilateral and move one of the detectors around and kind of map out some tripole structure. Or you can take some kind of 4-point where you rotate the inner ones and map out this nice structure. And similarly, by rotating about, for example, endpoints. And so you kind of map out this very nice picture of the energy flow within jets. And so this provides you access to kind of OPE limits, spinning operators, and a whole kind of wealth of very nice things. And so as I mentioned, the thing which is really cool is that this can actually be measured. And so this is being done by these people at MIT who worked very hard this last weekend to make this plot finished. And so you can really actually, inside high-energy jets, measure, for example, these 4-point correlation functions. And so in this plot, these 2 energy correlators out here are kind of fixed, and then it's rotating or spinning these inner 2 shown here. And so you can very nicely see, for example, this OPE singularity in the middle, and then additional OPE singularities as these kind of approach the endpoint. And so you can really kind of measure very precisely these higher point correlation functions and just kind of play with them and test them against predictions from QCD. And so this is just another measurement of this where you spin this around this particular axis. And so it gives you a kind of very nice access, for example, to this OP limit and the structure of operators that appear there. And so I think this really motivates exploring the higher order perturbative structure of these observables. It's kind of a very nice playground for looking for structures in real world physical observables. Okay. So now that one can have these, I just want to highlight a few kind of phenomenological applications of where these are useful for understanding more complicated systems. And so in these, one typically does not have an understanding or you just can't compute them in perturbation theory, but I want to show that they can be very useful to experimentalists, and by understanding very well or having an intuition of how these behave in either QCD and perturbation theory or in simpler theories, you can start to understand more complicated systems, and they're very useful for experimentalists. So just as 2 examples which I want to highlight, or one, how these can be used to kind of image or understand energy flux coming from the structure of the quark-gluon plasma. And the second is how you can use these to try and make precision measurements of the mass of the top quark. Okay, so as people are probably aware, so heavy ion collisions at the LHC provide the opportunity to study these energy correlators in thermal states. And so what you do is you produce some jet which goes through your kind of quark-gluon plasma, and this produces some imprint of interesting structures which will appear in the energy flux in infinity. And so this is something which you have very poor control over theoretically, but experimentalists can go out and kind of measure the structure of these correlators, and one can compare with what one has at weak coupling. And so the first thing which one can do, and so for now the measurements will be coming out soon, this is just using simulations. The first thing one can do is to study, for example, the 2-point correlation function. And so the very nice thing is because you have this angular lever, what you can do is at very small angles, this is a kind of a particle or something which passed through the quark-gluon plasma and then split very near to the boundary at asymptotic infinity. But as you kind of pull these apart, you essentially push this object back into this little ball of plasma in the center of your collision, and you can really see an abrupt, so earlier I showed this nice scaling behavior in the vacuum, and you see this real kind of abrupt transition as you pass into the quark-gluon plasma. And so by measuring kind of higher point correlation functions in this region, you can then kind of map out the structure or the interactions with the quark-gluon plasma. And so this is just an example of a simulation of a 3-point correlation function and the ratio between what I showed earlier or in the quark-gluon plasma compared to the vacuum. And so earlier it had only these nice operator product expansion limits which are down here. But so now it has this very nice kind of enhancement coming from the kind of strongly coupled wake that you're interacting with. And so these are things which have now been measured, and although one can't yet compute these things, they're very interesting for understanding how the core coolant plasma interacts with QCD jets. And so I think these also really motivate trying to understand the structure of these observables in thermal or very large charged states. And so there's been some nice recent work on this. So one is using these very heavy half BPS operators in n=4. And so here you can really compute this as a function of this k. So you're producing kind of many, many, many states. And you can see that it converges. This is, sorry, a bit bad, but it converges to this kind of flat or asymptotic behavior, which I showed at strong coupling. And then there's also been some progress in computing these in large charged states using a semi-classical description in terms of superfluid effective field theory. And so here again, one gets this uniform distribution plus corrections. And so it'll be very interesting to try and actually compute these corrections and understand these. And so again, I'll just flash this very quickly. So another application is to try and measure very precisely the mass of the top quark. And so this will imprint itself in some particular pattern in this 3-point correlator. And this is kind of actually very similar to what happens, for example, in cosmology. And so you have some particular imprint of the top quark mass in a kind of equilateral configuration from this underlying hard process. And then you have an imprint of the mass of the W from this kind of squeezed limit where you see the on-shell W propagating. And so this is just to show that this is something which can be done, but you can very accurately, or you can kind of map out experimentally the shape of this 3-point correlation function, which is now much more complicated than the one which I showed before. And so from this, you can actually very precisely extract the mass of the top quark relative to the W quark, or the W boson. And so to improve this really requires kind of precision calculations of these high point energy correlators on top decays, and is also a very clear target for improved perturbative precision. And so finally, in the last few minutes, I just want to show briefly what one gets when one really goes away from this conformal regime. And so that you can really actually very nicely see, for example, the effects of confinement, and that QCD is not a conformal field theory. And so in the plots before, I was always cutting off the very small angle, or the IR region. And so earlier I showed this kind of where you could extract the scaling behavior very precisely in this region. And so it had this nice non-integer scaling, which you can compute in terms of these anomalous dimensions in the light ray OPE. But you see that as you move to very small angles, you just very clearly see this sharp confinement transition where you rearrange into hadrons. And then on this side, you actually just have a kind of integer power law scaling and trivial higher point correlation functions. And this is just the kind of free hadrons propagating out into your detector. And so this provides a kind of very nice way of imaging this confinement transition. And so one could ask whether, or it would be very interesting to understand whether there are models where this transition is really computable. And there's some nice recent work by Chav and collaborators on trying to do this using some IR brain model, but of course, it would be nice to understand this more quantitatively. And since I only have 1 minute left, I'll just skip these two. And so one thing I just wanted to say is that these kind of measurements at the very, or all these measurements at the LHC have motivated a reanalysis of old Aleph data. So earlier I kind of said that it was nice to move from LEP to the LHC because of the very high energies, but now you can actually go back because it's extremely clean. And so this is an extremely precise measurement, which is coming out from the group at MIT of the 2-point correlation functions measured on tracks, which what I skipped is that we can actually understand how to compute these with extremely spectacular resolution. And so this is the kind of old measurement from LEP, where essentially this entire kind of 1 point is now these like 100 bins over here. And so you can very nicely map out a kind of huge regime of different ranges in QCD, going from the hard perturbative scattering in the UV to these different light ray or Wilson line operator product expansions to this universal scaling in terms of hadron gases on either side. So this is a very nice and very clear target for very precise calculations of these 2-point correlation functions in QCD, which people should extend the nice ones in n=4 to very accurately describe this. And so just to conclude, so there's been a lot of recent progress on understanding these correlation functions of detector operators, both from explicit perturbative calculations and from the CFT perspective. So these can really be very precisely measured at the LHC. So I showed these nice measurements of the scaling behavior that you can extract the strong coupling from, as well as of higher point correlation functions where you can see their shape. And so this provides a very nice opportunity to kind of theoretically use these very nice, beautiful objects to learn about real-world physics. And so I don't have time to go through, but I left a kind of bunch of open questions on trying to better understand these. So although there's been a lot of progress, there's still many questions to be answered. And so these are kind of the questions from the phenomenologist side. Oh no. But there was also a very nice talk by David Simmons-Duffin from the kind of conformal field theorist side, which is asking a lot of the kind of similar questions, and in particular, how you measure general collider operators or general detector operators at collider. And so I think this really shows there's a very nice kind of interplay of these techniques from Amplitudes, conformal field theory, and real-world collider physics, and that these conformal colliders have really made it to the LHC very nicely. So thank you, and sorry for going over time.
Thanks, Ian, for this wonderful talk. So, are there any questions, please?
Hey, is it me or somebody else? Okay. Thanks for this great talk, Ian. Very wide-ranging. One thing you maybe didn't touch on too much is sort of flavor dependence, and that both means how does the flavor dependence of the splitting affect the alpha S extractions, and also the possible use of the flavor dependence to do jet tagging and flavor separation.
Good. So by flavor, you mean like quark versus gluon. Yeah. So if I go back to, so that's a very good question. Sorry. So I didn't discuss too much because I kind of glossed over this. So as you know, or because these scale with these different anomalous dimensions are larger when you have higher fractions of gluons and smaller when you have quarks. And so for doing the precision alpha S extraction, this could be problematic because they're kind of degenerate with the quark-gluon composition. And so I should say that the actual or the leading uncertainty from the theory side here is exactly calculating that quark versus gluon. So this fraction comes from the hard function. So if you assume the PDFs are good, then this is what you have to compute. And so the remaining leading uncertainty on these is really coming from that fraction. And so I think this is something which can definitely be improved more. And so one could also worry about whether there's large contributions from changes in the PDFs. And so for this, by taking this ratio, this seems to be quite robust to these effects. And so this is definitely true if one just uses like the 2-point correlation function, that there's a decent degeneracy with changing quark-gluon fractions. But once you take this ratio, they tested quite systematically PDFs, and this didn't seem to have a big effect. And I mean, the other thing which would be very nice, which they can also do, is you can measure ratios of like the 4-point to 2-point. These are all predicted in terms of the given initial state, because the anomalous dimensions are all fixed once you fix the external state. And this could further kind of extract this degeneracy. And so I think that would be the most convincing thing to really show that you do that, is to do this systematically over a variety of, because then it's a very over-constrained system. Yeah.
Thank you. I have a question about the measurement of non-Gaussianity on accelerators.
Yeah.
In CMB, we have different cosmological models of inflation, which predict different values of different kind of non-Gaussianities.
Yes.
Now, on accelerators, the goal of measuring, do you have models which will be distinguished, which predict different non-Gaussianities?
So that's a very good question. So when one does this, let's say just in vacuum QCD, I would say this is more to illustrate that we have control over the S0. So as you say, we believe this is very well described by QCD, and so it's just showing that we can compute it and actually measure it and understand it. And so this is just an illustration that we kind of, in some sense, understand what we're doing and are able to describe things to this level of detail. But then where one wants to actually use it to extract something is, for example, in these quark-gluon plasma examples. So here I showed a particular simulation. So this is actually from Krishna's group at MIT of using some strongly coupled n=4 for the weight. So here you have essentially no idea of what's going on. And so if you do this in different models, they give very different shapes of the non-Gaussianities. And so I think this is where what you want is a very detailed understanding of like vacuum QCD, which you should just compute in perturbation theory. And then you look for how it's modified but in other systems where you have less control. And that's where it actually is kind of experimentally interesting.
Okay.
So that's a very good point. And,
Thank
and
you.
if you do this in different models, they give wildly different, because there's very little understanding of how to actually do calculations with the quark gluon plasma. And so they give wildly different answers. And so I think experimentally, this will be very useful for at least distinguishing between different models.
Okay, thanks.
I guess.